basically asking yourself if the population of a certain number is equal to what you think it might be. In this case, we're using the population is equal to the random number table, so the population that's a good average is truly 4.5. We happen to know, as a side fact, that the sigma is truly 2.87, but realize that number will not be available to you, and we have to sort of deal with that. Later on today, we'll do that. So the decision, if the average truly is 4.5, which is called the null hypothesis, or the alternative hypothesis called H1, if the average is the opposite, namely not 4.5, that hypothesis testing, bigger, that hypothesis testing could be seen as a one versus the other, because two opposite points of view, will be determined by taking a sample from the population. And of course, the larger the sample, the better, but we'll take a sample of 5, just to make the number go quickly. And look at the average, of course, to the sample. I mean, that's not obvious. I mean, if you think about it for a second, you see, take the 5 numbers, but then take an average of the numbers. So we're taking the average. And if the philosophy is, if it's close to 4.5, we're going to say the H0 is true. And if it's far from 4.5, we'll say the H1 is true. Because we recognized last time, especially if you give the benefit of the doubt to the A0, you never expect the average to be perfectly 4.5. That's too much to expect. It's only a small sample, so you never expect perfection. So if you give the guy the benefit of the doubt, that boils down to saying that if it's close to 4.5, then we're going to accept the A0, or technically do not reject the A0. So what about 4.6? What about 4.7? What about 4.8? And what about 8.8? And we discussed this last time. And we said, well, 8.8 is clearly, if x bar is equals 8.8, that implies the H1. If x bar equals 4.8, that implies the A0. Because 8.8 is so unusual, especially through your experience with the Spitter project to date, that you'd have to say that the answer is something's wrong with the table, namely the H1 is right. So at what point would you change your vote? And that was what we discussed last time at length. We'll do it again. The numbers that some people came up with were 3.5 and 5.5, meaning if you're past 5.5 already, that's far from 4.5. So we said it this way. 3.5 to 5.5 represented the accept A0 region, and anything past this point was H1. H1, again, more or less repeating what I did last time. So how do you decide a 3.5 and 5.5, which were just guesses? There's nothing was magical about these numbers. Whoever came up with these numbers just took a random guess from one. But how do you decide if it's right or wrong? Well, you go through the mathematics of chapter 7 again, and you put down the population. But you put down the population giving the benefit of the doubt to the A0, under it, we call it technically, under A0, under the assumption of A0. In which case, well, it's a uniform distribution from 0 to 9, with a middle value of 4.5. We're postulating that the population truly is a good population, a good random number table. We happen to know the spread is 2.87. And if somebody would, in fact, hypothetically take 5 numbers from that kind of a population, like spin the spinner 5 times, or get a 3, 0, 7, 9, 6, whatever, and calculate the average, and place that average on a histogram, like between 2 to 3, 3 to 4, 4 to 5, you'll get it. If you do it a second time, and a third time, and a fourth time, and a millionth time, eventually all that picture that you come, the results from that, namely the picture of the x bars, called the sampling distribution of the mean, will have a bell-shaped curve according to either common sense, experience, and mathematical central limit theorem. The middle value, if the A0 is true here, then the A0 should be true here as well, namely that it's, if you continue to believe the A0 is true, so then the average of the averages should cluster around that same middle number over here, 4.5. And furthermore, we know, just by our knowledge of chapter 7, that the amount of spread predicted from average to average, if the A0 is true or false, this has nothing to do with the A0, is 287 over 5, which is 128, which is 128. And now we can actually check out to see if 3.5 and 5.5 are reasonable as an initial guess for the boundaries between accepting and rejecting. So 5.8 is over here. The 5.5 is roughly over here. And 3.5 is roughly over here. And between here and here, we can say this is the accept region, just translating these numbers into a different picture. But instead of saying accept A0, I'm going to say do not reject A0. Which, if you think about it, it's just the same thing. just more properly. But if you end up out here, you end up rejecting A0. And if you end up out here, meaning past 3.5, you reject A0. So the decision, if this pair of numbers is a good pair of numbers, is based on very practical considerations. If it gives us the right answer a lot of high percentage of the time, and we don't expect 100% because we're dealing with random numbers here, we're dealing with a small sample, so we can't expect perfection. But if it gives us the right answer a high percentage of the time, then it's a good choice for a pair of numbers representing the boundary between A0 and A1. If it gives us the wrong answer a high percentage of the time, then it's a bad boundary. That's a very simple and very logical decision rule to make to yourself. So what we did last time was we actually calculated how often, if the table is truly a good table, would we end up just by bad luck into the rejection region. In other words, what is the probability of rejecting the A0 when the A0 really is true, which in our example boils down to what's the probability of getting an X bar bigger than 5.5 or lower than 3.5. Or X bar. So when in fact the average is truly 4.5. And we know from the spinner assignment that is certainly possible. Many people, again, if we have to stand back and not to be cynical and say, well, our random number table or Excel is a good random number table. Yet when you pick 5 numbers out of that table, you sometimes get a 5.6 or a 5.8 or a 6.2. Anybody who did the assignment realizes that. So it is possible for this to happen. The only question is how possible, what's the probability? And this, of course, we call a type 1 error. And all these 3 things are called alpha. So alpha is the probability of the type 1 error. Alpha is the probability of rejecting A0 and A0 is true. Alpha, in this case, is the probability of this actually happening. Alpha is PHA. Alpha is sometimes called the significance level. And alpha is sometimes called the size of the region of rejection. So it goes by many different names. It all means the same thing. The question is, what is alpha in this particular case? And if alpha turns out to be a high number, then we have to modify our boundaries. And we did last time by going to the Z diagram. Again, what I'm doing is repeating the last lecture, which in turn was repeating chapter 7. So we did this exact same calculation with the same pictures in chapter 7. Here we have a bell-shaped curve, and the standard normal distribution. You want to convert the 5.5 to a corresponding z-score. The formula to use is x bar minus mu of x bar over sigma of x bar. No coincidence, I think it's the exact same formula over here. And in this case, the number we're plugging in, since it's we can plug in a 3.5 or a 5.5 or both, one at a time. Let's do 5.5 first, minus 4.5 over 1.28. Which in turn equals 1 over 1, we said it was 0.70 something yesterday, what did we say last time? 0.70, 78, thank you. And 78 is where on the diagram? Well, it's about 3/4 away, which is around here. And we want to figure out this becomes the reject region when you translate it to the Z diagram. This is, if you plug in a 3.5, I can guarantee you're going to get a minus 78. So the reject region translates over here as the area, in other words, the area to the left of 3.5 is comparable to the area to the left of minus 78. And the middle part will continue to be, do not reject A0, so you do not reject A0. So the only question is, that in order to figure out the alpha, which is our goal right now, in order to determine if this pair of numbers is good or bad, excuse me, hello? I'm in the middle of class. Fine. Okay, I figured a call from the house must be important because I know I'm in class. But I guess okay. What was I saying? I was saying we're trying to figure out the probability of this thing happening, meaning we're figuring out the alpha, and then you look up minus 78 in the back of it. Now, what's the area to the minus 70, to the left of minus 78? We did it last time. I think we came out to 0.22. What did we come out to? 21. Again, anybody who hasn't been using the Z table in all their previous homeworks, and you should actually take out the table, you should have the table with you.